The universe is expanding, and we know that because when astronomers look out at the galaxies around us, they see every galaxy moving away from us at a speed that increases in proportion to the distance. It doesn't mean that there's anything wrong about us, that everybody's moving away from us, or that we're at the center of the universe. Any other hypothetical observer in any other galaxy would observe exactly the same phenomenon. It's a remarkable fact of our universe. It is expanding. Now, that amazing phenomenon was discovered by this man who had a number of problems. He was Belgian, he was a priest, he was a Catholic priest, and he wrote his papers in French. So they were thoroughly ignored. It's about 100 years ago, until 2 years later, an American, of course, Edwin Hubble, rediscovered the same thing that Lemaitre had. And finally, in the last few years, the International Astronomical Union decided to rename Hubble's law as the Hubble-Lemaitre law. So our universe is expanding. You don't need to be a rocket scientist to conclude that in the past it would have been smaller. And in the very distant past, it would have been very, very small indeed. In fact, so small that all the billions of stars in the billions of galaxies in the universe would all be concentrated in a very small region the size of a pinpoint. And that region was very dense, very hot, and that's what we call the Big Bang. And now we know that the Big Bang happened 13.7 billion years ago. Now, I'm talking about physics, not about philosophy or art. And physics, for something to be physics, it has to be testable. So how do we test the idea that there was a Big Bang that we have just inferred? Well, we resort to physics, and we know from physics that as this energy from the early universe, as the universe expands, it will cool. And in fact, it turns out that the early universe was foggy, but when it was 350,000 years, which would be, in human terms, the equivalent of a one-day-old baby, then the fog of the Big Bang lifted, and this radiation was free to escape, and it is the first light emitted by our universe. Well, this light traveled for 13.4 billion years until these two lucky gentlemen, Arno Penzias and Bob Wilson, discovered it. They intercepted in the radio telescope this light that had been traveling to us from the Big Bang. And it was completely accidental. They were radio astronomers. They were trying to look at the sun. They were really annoyed that wherever they pointed the telescope, there was this hiss. And in fact, coming from everywhere, they had actually discovered nothing else than the Big Bang. The universe is so old that the radiation has cooled to very low temperatures, and today it appears in the form of microwaves as something we call the cosmic microwave background. Well, that was quite a discovery, but at the turn of last century, in a truly millenary discovery, we discovered something worse, we meaning cosmologists, about the expansion of our universe. Not only is the universe expanding, not only are galaxies moving away from us, but the speed at which the expansion is happening is accelerating. That is to say, if you take two galaxies today that are receding from one another at some speed, come back in a billion years, a little bit older than you are now, and you'll find that the speed has increased by quite a lot. That's what we mean by the accelerated expansion. So it looks like the universe is full of something that is pushing something that is causing this accelerated expansion. Now, in physics, when we don't understand something, we give it a good name, a magical name that allows us to put in compelling grand proposals. We call this dark energy. Now, so to understand why the universe is doing this bizarre fact, then we need to understand what the universe is made of. And another of the fantastic discoveries of the last 25 years is encapsulated in this graph. It turns out that the contents of our universe are really, really bizarre. Only 5% of what the universe contains is made of the ordinary atoms of which you and me and the Earth and stars are made of, the atoms of the periodic table of the elements. That's only 5% of what the universe contains. 25% is something we call dark matter, which, as the name indicates, is dark. It doesn't shine in any wavelength, and that's 25% of what the universe contains. And the lion's share, however, is this green sector here, the dark energy, something that opposes gravity, and it's pushing our universe, causing the acceleration to become, the expansion to become accelerated. So, dark matter is simple compared to dark energy. It's almost certainly a particle that was created very soon after the Big Bang. This plot is not on scale. It's not to scale. So this dark matter is a particle that was probably produced when the universe was tiny fraction of a second old. And we collectively call these particles cold dark matter. So cold dark matter is the basis of our understanding of a lot of the universe today. So that's easy compared to dark energy. So we conclude then from the accelerated expansion that the universe is full of dark energy. And what do you do when you have something you don't understand? Well, you appeal to your elders and betters, and who's older and better than any of us than the great Albert Einstein, whose picture you see here and whose equation you see there. Now, I'm not going to ask anybody to come to the stage and solve it. I'm not even going to ask you to understand it. I just want you to look at it, because for us physicists, this is beauty personified. Why? Well, because it relates on the left-hand side the curvature of space-time. In relativity, space-time is curved. That's what the left-hand side tells us. And the right-hand side describes the contents of the universe. And so I think everybody, just like everybody, at least once in their lifetime should see a Rembrandt picture, listen to a Beethoven symphony. At least once in your life, you should see this beautiful equation. And the last term in the equation was kind of half-heartedly introduced by Einstein. And it turns out that this could be the clue to what is the dark energy. So that Greek letter lambda is called Einstein's cosmological constant. And in fact, it turns out that it does exactly the job required. It will cause the accelerated expansion of the universe. And that does the job and led to something we call the standard model of cosmology, also known as lambda CDM, where lambda is Einstein, CDM stands for cold dark matter. And this model was introduced 25 years ago, and it has been the foundation of all of modern cosmology. Fortunately, I'm going to tell you in a minute that it's actually broken. But how do we test it? Well, first of all, we need to know what the model predicts. And over the last 40 years or so, we developed a very useful technique to understand what the model predicts, and that is to try to understand how the universe came to be the way it is. And we do that using a big computer. And what we do with the computers is we teach them physics. To solve the equations of physics. It's a lot easier to teach a computer than it is to teach an undergraduate at Durham University. And they work on weekends as well. They never stop. They never complain. They never lack. They just work all the time. They're wonderful. And you program a computer to solve those equations of physics, and then out comes the virtual universe. So let me show you a movie that came out of our computer here in Durham. And as you know, this was done in Munich. The next one is in Durham. And here's what you would see if you were able to wear dark matter glasses and travel at a speed much greater than the speed of light. You will see that the dark matter, which is what we see here, collapses or condenses into lumps. Those lumps are known as halos. And this is where galaxies will form inside these dark matter halos that arrange themselves in this wonderful configuration that we refer to as the cosmic web. Now, so that was dark matter, and recently we've also been able to simulate in a computer, it's a much harder problem, not just the evolution of the dark matter, but also the evolution of that 5%, the ordinary matter, which in many ways for us is the most interesting part, because that's what we're made of. And here you see a simulation. This was done in Durham, in our supercomputer here, and you can see that what you see here is the ordinary matter, gas, and everything is spinning in the universe. This is a very early universe, just 1 billion years after the Big Bang. And you see these objects forming, and because they're spinning, they become very flat, and they develop something that looks a lot like spiral arms. So there is one of the things that came out of our computer. These are the stars, a very thin disk of stars. And then as time goes by, this grows. The universe is a hostile place. It gets bombarded by all sorts of fragments that fall into it, but it can resist, and it becomes a stable object that becomes very thin and looks, maybe for some of you, might remind you of galaxies in the universe. And if you don't remember, I'm going to show you some in a minute. So here is, we're now going to cut to stars, and it produces a very thin disk with a bulge in the center. and this is happening everywhere in the universe. So here's a picture of the real universe taken by the Hubble Space Telescope. And here's a picture that I love, because I like to show this to my colleagues, observational astronomers, and I say to them innocently, "So where do you think these galaxies come from? Do you think they came from the Baculor survey or the Dark Sky survey?" And they scratch their head. No, I think this is the Zwicky survey. Wrong. These don't exist in the universe. This came out of my computer. And they look indistinguishable from the real things, to the extent that I can fool some of my observational colleagues into thinking they're actually real galaxies. And that's what you get from teaching physics to a computer and assuming cosmological constant and assuming cold dark matter. So the model, lambda CDM, has been tested against a huge range of astronomical data. What we find until now is that this model was consistent with a huge amount of data that I don't have time to describe. However, that was the story until 2 years ago. 2 years ago, after 10 years of work, we managed to come up with a way to test the theory to an accuracy of 1%. And I'll tell you what I mean by that, using a telescope in Arizona called the Mayowl telescope, which, as Herb said, has 5,000 little robots that position fiber optics in the focal plane, so that instead of, when you point this telescope, just being able to measure one galaxy, now you can measure 5,000 galaxies at a time, and that gives you, of course, a huge advantage. So what did we find? Well, it was published in the front cover of the New York Times last year, April 2024, a tantalizing hint that astronomers got dark energy all wrong. The BBC are not going to be outdone by the New York Times. A year later, actually, it's because we did another press release, dark energy experiment challenges Einstein's theory of the universe. What does that mean? And what is actually going on? Well, first of all, this instrument called DESI, Dark Energy Spectroscopic Instrument, has now measured data distances to more than 40 million galaxies. And this next statement here, even I find this awesome, that we can now measure the expansion history of the universe to a precision of 1%. So we know how fast the universe was expanding 10 billion years ago, 12 billion years ago, with a precision of 1%. When you have such precision, then you can do precise tests of the theory. And what we find is, in fact, that the data seem to be incompatible with the standard model. So we seem to have broken it, and it looks like though we're missing something very fundamental about our universe. Still tentative, it could still change, science evolves, but that's what the data are telling us today. So we need a new paradigm to describe our universe. So it's not the end of the world. The image that comes to my head is this one. Durham Cathedral here needed some repair. There was something broken, and it had to be repaired. And in physics, if this is the edifice of physics, we don't know what's broken. Relativity may be broken. Quantum physics may be broken. What we do know is that there's something very fundamental that we're missing about our universe. Now, so stay tuned. I don't know what the answer is yet. And not all my colleagues would agree with what I'm saying, but I've looked at the data carefully. And to me, we do need to change something very fundamental about the way in which we understand the universe. However, one thing that we do know is gives us a big hint of how our universe will end. So the reason for this is that the future of our universe depends on the behavior of the dark energy. And there are three possible fates that depend on how the dark energy behaves, illustrated here. The one on the right is if the dark energy increased, and we know it's not doing that, but if it increased, that would be a horrible end for the universe, because the universe will just rip itself apart in a phenomenon that very elegantly physicists refer to as a big rip. That's not going to happen. If it was Einstein's cosmological constant, the future would be pretty grim as well, because the universe would just continue expanding forever and ever and ever. Everything would decay. It would become a vast frozen expanse in something that we call the heat death of the universe. And that was the standard model until we broke it. And now, what I find very appealing is that it looks like the dark energy is declining with time. And we're in this regime here on the left. If the dark energy decreases with time, then the universe will continue expanding. The dark energy is getting less and less important. It'll stop pushing, and eventually our universe will recollapse, reach a maximum size, recollapse, and perhaps start again in a new universe. Going through a big crunch, and perhaps there'll be cycles of big bangs forever and ever. And to me, philosophically, that's a lot more appealing than a big rip or a heat death. But don't hold your breath. This is not going to happen for another 30 billion years. Thank you.